Hi everyone, I'm CHR Chuck and I'll be presenting our CPP 2021 paper towards formally verified compilation of tag-based policy enforcement. So let's talk hardware. The new 30 series GeForce graphics cards were just released a few months ago and everybody wants one. To train their deep neural networks, to mine bitcoins, and in some rare cases, to play high-end computer games. Okay, but we can also use hardware to improve security, not just performance or compute-intensive tasks. We could improve security in legacy software, especially in unsafe languages like C, C++, by having a reference monitor run in hardware at the end of the compilation toolchain. This, in theory, would save us from having to make too many changes to the source code. Addressing these safety issues can also be done in software, but this is going to be prohibitively expensive, and hardware can help decrease that overhead. Let me remind you what a reference monitor is. It monitors the system and intervenes to stop bad behavior by fail-stopping the system. The definition of what behavior is bad effectively defines a policy enforced by the monitor. We want monitors to be always invoked and non-bypassable, meaning that every system operation must be explicitly checked for bad behavior. Reference monitors are good at enforcing safety properties. Intuitively, we have safety when bad things never happen. For example, in C, we might want to monitor that we never dereference unallocated or freed memory. Here are some examples of safety policies. We have a secrecy policy that wants to ensure secret data is never leaked to public channels. This is going to be an example of an information flow control or IFC policy. We have a heap safety policy that might ensure stores only access valid memory locations. This is part of the general class of memory safety policies. A last example, ensuring that modules communicate only via their APIs, would harden components by decreasing their attack surfaces. This example belongs to the general class of compartmentalization policies. All right, I want to introduce you to the hardware reference monitor our work is building on, called Pipe. Here we have a typical microprocessor design containing an instruction store, a register file, access to memory. Pipe is an architecture extension that gives all of these components metadata tags. That would be the green parts of the diagram. So in the register file and the memory. And I particularly want to call out that the PC is given a tag as well. These tags are going to be large, roughly the size of the corresponding data. Secondly, Pipe also includes a TMU, the tag management unit, which is the main mechanism for monitoring. Just as the ALU gets data, the TMU will get the data's corresponding tags, and via that information, enforce a policy. I want to emphasize that the data paths for the ALU and the TMU are similar. When the ALU gets operands from the reg file, the TMU gets the tags on those operands. When the ALU gets data from memory, the TMU gets the memory locations tags. So too with the output data paths. Values written to the reg file or stored by the ALU are tagged by the outputs of the TMU. In particular, the TMU will always get the PC tag and always produce a next PC tag as well. Pipe is very flexible and general. It allows the end user, who we'll call the security engineer, imagine someone tasked with hardening a legacy code base. It allows the security engineer to define tag sets and policies over those tags. This flexibility also allows policies to be combined or run in conjunction with one another. So for example, you could write a policy that provided both memory safety and compartmentalization. Pipe satisfies the qualities we said we were looking for in reference monitors because it runs at a per instruction granularity, no code is left unchecked, and because it runs at the machine level and therefore can't be evaded by malicious software. Pipe has been developed under the aegis of several DARPA projects, and various IPs incorporating its designs are also available commercially. Since Pipe operates at the per instruction granularity, this means each instruction invokes a tag rule executed by the TMU, just as an instruction is executed by the CPU. To see an example, consider the signature of the add rule here. Note that a bar indicates a tag rule and its corresponding instruction. Add bar is the rule corresponding to add, and BEQ bar is the rule corresponding to BEQ. So add takes the contents of R1 and R2, writes their addition into RD. Similarly, add bar takes the tags on registers R1 and R2, here given by T1 and T2, and produces a destination tag, TD, that will be used to tag the register RD. Remember that rules can fail stop, noted by the red FS over here. And again, analogous to regular instructions, add bar also updates the PC tag from value P to P prime. The PC tag is typically used to track ambient metadata about control flow or program context. Lastly, tag rules also take an instruction tag, here given by TI. Instruction tags contain metadata about instructions. For example, it might record provenance, telling us whether an add was compiled from an expression or from pointer arithmetic. In the BEQ case, there's no destination register, so BEQ bar only produces a new PC tag. For performance, the TMU acts like a cache, keyed over the tag rules and their arguments like we saw on the last slide. Misses will trap control into a tag mishandler, which will invoke the actual tag rules, i.e. execute the policy. Just as different regular or untagged programs admit different amounts of iCache overhead, so do different policies and program patterns admit varying TMU overhead. That said, simulations using Spec 2006 benchmarks running fairly rich composite policies only incurred less than 10% overhead. Let's look at an example, an abstract version of an IFC secrecy policy. In this policy, data is either secret or public, and any operation involving secret data produces secret output. The key property we want to enforce is that the secret data is never leaked on public channels. Another issue that IFC policies need to prevent are implicit flows. What's an implicit flow? Consider this conditional here. Neither arm leaks secrets, but by examining which arm is taken, i.e. whether a 1 or a 0 is written, we can learn something about the value of secret B, which is a secret variable being tested. To discuss secrecy policies, we'll use standard lattice notation such as meet and join, where true in the lattice is given by secret and false is given by public. So here's what this secrecy policy would look like at the pipe level. First of all, we're going to have the PC tag track a security context. The security context starts as public, and a test may raise this security context to secret to prevent an implicit flow. We can see that in this BEQ rule. If any of the compared operands or the PC tag or the input PC tag is secret, so too is the output PC tag. We can see a similar thing happening with the add rule's output destination tag. Although the add rule can just leave the security context as it found it. One thing the pipe policy cannot do is delimit this implicit flow. What do we mean by delimit? Consider how, once we are done testing a secret value, we might like to restore the security context to what it was before the test. However, join points are not visible at the machine level, so we won't know when to restore the previous security level. So we get a form of label creep, where once BEQ raises the security context to secret, there's no way to lower it. So we see that low-level policies can have some drawbacks. Some policies are difficult, even impossible to define at machine level, because abstractions such as split and join points, argument passing, and function level structure just aren't visible. This means that machine-level policies require knowledge of the tool chain. For example, a stack safety policy is going to need to know how the compiler lays out the stack. In short, policy definition at this level can be tedious and error-prone. We can, however, address that by compiling high-level policies to pipe. At the high level, more policies will be expressible since we have access to more abstractions. And they should also be more easily expressed, just as it's easier to code in C than in assembly. However, that means taking the compiler into the trusted computing base. The TCB are those components that must be correct for security guarantees to hold. And so, of course, the compiler should now be verified. Though perhaps at CPP, we shouldn't need such a reason to verify it anyway. Okay, but what would a high-level policy look like? First, we're going to need to describe where monitor checks will happen. We can do that by augmenting a high-level language with control points, indicated in this diagram by blue arrows. Every blue arrow indicates a place we might invoke a tag rule. because these are places where computations happen. With that, we can consider how a high-level secrecy policy might treat conditionals. Conditionals here have two control points, one for split, one for join. The split rule is similar to the BEQ rule in that it propagates the secrecy of the PC or any of its operand tags. In fact, its body has the same definition as the BEQ rule. This serves to prevent implicit flows. We also see that the high-level plus rule is again extremely similar to the machine-level add rule. The interesting case here is in the join rule, which takes both the current PC tag P as well as the PC tag at the split point, here given by PS. The rule then simply restores the output PC tag to be PS. In this way, it can delimit implicit flows. Tagine is our verified pipe-aware prototype compiler. It preserves fail-stop behavior throughout the toolchain. That is, if a source program fail-stops, so does the target, thereby guaranteeing policy enforcement. Of course, it also verifies the usual compiler correctness. To do this, it has to instrument IRs, the intermediate representations of the compiler, to be tag-aware. We'll look at two IRs. The first, HLL, represents high-level languages. It is a simple imperative language comparable to while or imp, but with functions. RTLT represents a toy or prototype version of machine code. It's simple enough to allow us to prototype quickly and understand the crux of the issues in introducing pipe concepts. But it's also realistic enough to illustrate the problems and challenges we would face in a more realistic setting. These two languages were adapted from ComCert IRs, C-cell and RTL. I'll present two passes in Tagine. The first is RTL Gen T, which translates from HLL to RTL T. This is adapted from ComCert's RTL Gen. This is a key pass in the toolchain, as it's the first pass going from a language with abstractions such as expressions and structured statements to an instruction-based language. We'll use instruction tags, or just I tags, that we saw earlier to preserve these abstractions. The second pass, which optimizes over RTLT, is DIDcode T, which is adapted from ComCert's DIDcode. For ease of the remainder of the presentation, I'll be dropping the T's from the Tagine passes and IRs. So from now on, when I say RTL Gen and DIDcode, I'm referring to Tagine's passes, not ComCert's. And when I say RTL, I'm really referring to Tagine's RTLT. Okay, let's have a quick look at HLL. The main thing here to observe is that now values are tagged, as can be seen in blue. We'll use the @ symbol to indicate that something is tagged. Also, all of the language constructs shown here have control points associated with them. So they're control points for variable reads and for operations, for assignments and function calls and returns, for example. Now let's look at RTL, and we'll focus on the left column first. First of all, we have some opcodes, which are pretty standard, but there are two things to take note of. The first is that registers now hold tag values, not just values. And we also see this in the move immediate instruction as well. The second is that instructions now take explicit successor instructions. This is because RTL is CFG based as well as instruction based. This leads us to the N and the G in the left column. Instructions have node labels, and graphs or CFGs just map these labels to instructions, and those instructions have been tagged with I tags. In the right column, however, we see the CFG fragment that results from the compilation of a binary operation. Let's first look at the white box with rounded corners, which represent individual instructions. We can see here the three elements we mentioned earlier: labels, instructions themselves, and their I tags. Gray rectangles with sharp corners, on the other hand, indicate CFG fragments, i.e. multiple instructions. Here, we see that the CFG at NE will store the tagged result of evaluating E1 into the register R1. This shows us both an example of CFGs as well as compilation. The key observation of RTL Gen's design is that we can use I tags to preserve high-level abstractions at the machine level. A corollary to this is that all we need to make compilation pipe aware is to tag instructions appropriately with the correct I tags. In particular, we shouldn't have to insert extra instructions, well, most of the time, but we'll come back to that. In the diagrams here, and note that the Oxford brackets indicate compilation. Both of these diagrams show that constants and variables are both compiled to mobs, but their I tags will tell us what they were compiled from. Another previous example that we used was that an add rules I tag can tell us whether it was compiled from expression evaluation or stack pointer arithmetic. Since the compiler must do this preservation of abstraction, I tags are mostly compiler defined. However, sometimes additional instructions are required to preserve high-level abstractions. If we look at the CFG fragment of this compiled if, we can recognize an if starting at node n1 through the two arms of the if. However, the instructions at NE and N4 are pseudo instructions that would enable the saving and restoring of the security context in an IFC policy, for example. Note that these control points are still general and are still triggered for any policy, not just IFC ones. This brings us to how preservation of source abstractions via I tags help us preserve fault stop behavior. First, we must note two things. To preserve policies or fault stop behavior, the RTL policy must be defined by RTLGen to invoke the HLL rules. We see an example of this in the con rule, which merely passes its arguments to an HLL level if split rule. Second, since I tags record provenance, RTL rules must dispatch not only on the opcodes, but on the I tags as well. This is seen with the two pseudo-mov instructions. The first saves the split point PC tag by saving that PC tag into TD, which will tag the destination register RD. The second mov instruction for join shows that same split point PC being retrieved, here given by TS, and it's passed on to the if join source rule. This works because the pseudo instructions have the same source and destination registers. I just want to underscore that RTLGen is abstract with respect to the HLL tag set and policy, but must define some injection, here given by mathcal_I, that builds the RTL tag set and policy with it. For example, RTLGen has to define the I tags that will go into the RTL tag set. Okay, now let's talk compiler correctness. The formalization of IR semantics is adapted from ComCert. However, Tajine's IRs do not have IO or traces. Only the final result of the program is observable. The IRs have transition or small step semantics. The semantic steps between program states. Program execution is just the path or steps that a program takes through this transition system. Then, we have several program behaviors as in ComCert, but we also add in a fail-stop behavior for policy enforcement. This notation here should be read that program S executing under policy P exhibits behavior B. While we're still in notation, just recall that the Oxford brackets represent compilation, so Oxford S here is the program resulting in the compilation of S. The results from the compilation of S. So the semantic preservation notion that we use for Tajine is refinement for safe programs. Refinement for safe programs states that compilation should not introduce new behaviors into the target. In other words, any behavior observed in the target program must be observable in the source program. Further, we're only interested in safe programs, which are those programs that do not go wrong. However, our top-level refinement theorem is proved by a forward simulation lemma. It says that every individual step in the source semantics between two states can be simulated in the target semantics between two states that match the source ones. It follows the standard simulation argument format. In the diagram here, solid lines represent hypotheses, while dashed lines represent proof obligations. Simulation arguments compare two programs, say a HLL1 and an RTL1, and examine their equivalence. The standard format says that if we know that an HLL program can step from program state H1 to H2, and that H1 matches RTL program state R1, we'll come to matching in a minute, and if we can then show the existence of an RTL program state R2 such that an RTL program steps from R1 to R2 and program state H2 matches R2, then we have shown that the HLL and RTL programs perform the same computations, that they are in some way equivalent. The notion of the sameness is derived entirely from the matching relation. Matching relations are often the most intricate and therefore interesting to the compiler verifier, part of semantic preservation, and I'll enthusiastically refer you to our paper for details. The matching relation also guarantees that the target program behavior will be the same as the source program behavior. A well-known result is that forward simulation in conjunction with target determinacy implies refinement. Next, let's discuss policy independence as a segue to optimizations. Policy independence is when a compiler pass does not require knowledge of the policy's rules. This has some benefits. It means that we can change a program's policy without recompilation, perhaps even while the program is running. It also means that the compiler passes definition and verification are easier. But policy independence blocks optimizations. The next section will show us why. The optimization pass we present is dead code, which removes computations that don't contribute to a function's final return value. In the paper, we also discuss common sub-expression elimination and constant propagation, which unfortunately are not verified passes of Tajin. So let's review code deadness. Here, the add is dead because its destination register is unused by the end of the function, so we can remove it. However, in a pipe setting, we might have add bar which may fail stop. And if there's even a chance it could fail stop, we cannot remove the rule, since we have to preserve fail stops. That's one example of a rule that isn't dead. Another would be if the rule changed the PC tag, as this could affect whether or not the next rule fail stops. This also reminds us that the PC tag can effectively encode state, since its definition is arbitrary. In fact, policy independence requires that source rule invocation sequences must be exactly the same as source embedded in target rule invocation sequences. However, this is far too restrictive for optimizations. The only way we'll be able to preserve fault stops when we know nothing about the rules is to make sure that the same rules are called in the same order. So to deal with this, optimization passes give up policy independence. Instead, they rely on policy properties. Such properties could be inferred from studying the policy, for example. However, the paper does not discuss this. It only describes the mechanism by which source rule properties are conveyed to target policies. So let's now look at a definition. So now let's define a notion of rule deadness. Two properties together will give us sufficient conditions. The first property is if the rule never fail stops, and we'll call this DFS for doesn't fail stop. It describes rules that always return tags and never fail stop. The second property is when a rule does not change the PC tag. Or in other words, the rule is side effect free apropos of the PC tag, which, as we said earlier, can encode state. We call this PCP for PC pure. It says that if the rule doesn't fail stop, then it must propagate the same PC tag. Now, these are obviously undecidable properties, but both are easy to approximate statically when looking at their definitions. For DFS, we can check that it never returns a tag error. And for PCP, we can just check that the output and input PC tag are syntactically equal. Together with the regular notion of instruction deadness, these two properties guarantee that no tag information is propagated from dead tagged instructions to subsequent tag rules. Policy properties form a general framework for pipe-aware optimizations. But recall that while policies are defined at source, we're really interested in the properties of RTL policies, since this is the IR over which optimizations take place. Just as with tag sets and policies, we also need RTL gen to inject the properties for us. This should be done in such a way that the RTL rules have property X only if the corresponding HLL rule does. Recall that I tags are needed to distinguish HLL rules compiled with the same instructions. So for example, excuse me. So for example, a MOV rule tagged with the I tag IT assign will only have the property DFS if the source level assign rule also is DFS. And of course, the injection of the properties must respect or mirror the injection of the policy itself. Once we have this framework of policy properties, however, we can also use it in RTL gen. It can help us to describe or discern when a rule is redundant. For example, many non-IFC policies do not require the if join rule or the if split rule, which would allow us to save on the pseudo instructions inserted for saves and joins if we could somehow get rid of these rules. Lastly, I want to discuss future work. There are several axes along which we could proceed. The most obvious is we need to extend our prototype to include full C control flow. Namely, we need to make our IRs more realistic. One open and interesting question here is whether IFC policies would be useful or even cogent in the presence of Go tools. Then, perhaps the most important is to add a notion of memory to the prototype. This would allow us to investigate memory safety and compartmentalization policies and the many significant optimizations over pointers. Next, we could also investigate applications of pipe. One such project, Concrete C, would use pipe to turn some memory UBs into fail stops. This would allow us to define a C variant which would be control safe, no return-oriented programming, for example, and would also allow the security engineer to trade off levels of memory safety for performance or vice versa. Our paper demonstrates a plausible design for high-level tag-based monitoring and its compilation to pipe-equipped hardware. We formalized a prototype compiler and verified that it preserves monitoring semantics. Although our formal development covers only a toy source language, it has allowed us to confirm the feasibility, the most novel aspects of the compilation approach. Lastly, we developed a framework to tackle pipe-aware optimizations. And that's our talk. Thanks very much.